Okay, I'm just waiting for my class to kick in to see some viewers, and I'm going to start. Today I'll be talking about how to differentiate between polar and nonpolar molecules, bonds, and writing some basic Lewis dot diagrams for a Regents chemistry class. I will be sharing my screen with the homework we had last night. So I'll be starting momentarily, waiting for my viewers to click in. Still hanging out by myself, waiting for my viewers to log in. And again, this is a Regents chemistry lesson, reviewing the concepts of polarity, specifically molecular polarity and bond polarity, three-dimensional shapes. Also reviewing how to use our models here to figure out the three-dimensionality. And I'm just waiting for my class to get settled and join me. Still waiting, speaking to no one, particularly with myself, and hope everyone has the same link. Just making sure it is the same link. Okay, I'm still just waiting for a few more viewers to chime in here, and we're ready to rock and roll. Looking to take out your homework from last night. I want to review that, and I also would like to review how to use those molecular model kits. I'm going to spend 20 or so minutes reviewing your homework, reinforcing what we did yesterday, and then we are going to I'm going to show you how to make sure we are on the same page in regarding to using these molecular model kits, which you're going to continue on throughout the rest of this period and next period. Okay. If you are using the Google Plus link, and again, I'm not sure if in fact it is working, okay, then you could chat me questions as we go. And again, I haven't run this or tried to run this with any class yet, so I don't know if it will be successful. But if there are any questions, the link to the classroom, the portal, okay, would be through Kelly. All right. So I have 11 viewers. People are sharing and so forth. Assuming everyone can hear me. And I'm going to take out the homework, and we're going to go over that together. Okay. So here we go. Let me share my screen and take out the homework. Assuming everyone can hear me loud and clear. Is that true, Kelly? That I'm coming through loud and clear? Just waiting for her response. You should have this worksheet out. Yours should be done. All right. But I want to show you how we would do this regarding with the models. All right. So we would first start with our elements. Okay, thank you for responding. Oops. Okay, so let's get started. I'm going to take you on the journey here through this worksheet, and it's going to look a lot like the lab you started Wednesday and continue to work on today. So let's start. So you should have an H. Oh, too big. All right, there we go. Should have an H here. Okay, and make that a little thicker. And we know H has one valence electron. Iodine, okay, has the 7, and we should know where that is. It has the 7 valence electrons. And of course, we're looking to fulfill the octet rule. And we can see clearly that iodine fulfills the 8 by sharing. It feels like it is as stable as a noble gas that has that 8. And hydrogen, okay, also has, well, not also, but has 2 because it has as many electrons as its noble gas in its energy level. It's showing 2. So by sharing, and again, I can't help but reinforce, this is a covalent bond because these two elements have high electronegativity. They're pulling on the rope, but nobody can truly win, so they're forced to share. They have similar electronegativities. Okay? All right, so the question is, what's the bond type? Well, we know it's covalent. All right, we know it's sharing for a couple different reasons. These are both nonmetals. And as we have looked, okay, previously, our nonmetals are above this staircase, right in this area. So we have iodine and we have hydrogen. Now, of course, hydrogen is that Waldo. It's put over here because of one valence electron, but it belongs with the other noble gases. All right, so these are two nonmetals, and nonmetals are forced to share because they're smaller. They attract their electrons. They're forced to. Okay, so back to where we were, okay, which was not that. Well, it was, but not that one. So here we go. All right, hold on. Where is my journal? Here we go. So here we go. So this is going to be what kind of bond? Well, I know these have different electronegativities because they're different. Hydrogen is at 2.2 if you look it up on table S, and I believe iodine's at 2.8. Okay, if you look it up, and I could be off there by a little bit, but I know they're different. So that means that this pair, okay, is a little closer to the iodine, which means it's sharing unequally, which means on the iodine side, it feels like it has more electrons than the hydrogen side. So we say this side's the negative part of the bond. So this is going to be a polar bond, a polar covalent bond. Why? And you better know the why, because they're sharing unequally. You can see it. Now, I drew it this way. You don't have to, but clearly they're sharing unequally. All right? Now, the molecule type. We talked about molecules. Molecules have an unequal distribution of electrons on one side than another. And the one side that has more rich electronegativity or more rich number of electrons is that partial negative side. The place missing it is that positive side. So my friends in chemistry, well, you look at this molecule, it only has one bond. And that bond is polar because of this unequal sharing. And the side that has more electrons has to be the negative side. And this is the positive side. So we would draw something called a dipole moment to show the charge. We go from the positive side to the negative side, okay? And if you don't quite get the dipole moments, I'm just pointing from the positive side to the negative side. And it shows a flow of charge, okay, a moment. This is a polar molecule. Now you may say, Mr. Grodski, didn't we have a rule yesterday to be a polar molecule? And you're absolutely right. To be a polar molecule, one, you have to have a polar bond. And this is a check. Clearly it's a polar bond, two different nonmetals, two different electronegativities sharing unequally. However, the second thing I said to you is you have to be asymmetrical to be a polar molecule. Well, this is asymmetrical. How do I know? Well, because it's different on both sides, all right? And it's asymmetrical. Now, my friends in chemistry, you may say, well, it only has one bond. Yeah, and like I said, if it has one bond, there's no other bond to cancel it, so it can't be nonpolar. There's no other bond for it to cancel. So therefore, this is a polar molecule because of its asymmetry and because it has one polar bond. But if you think with me, if I draw my circle, this is the place that has the high rich electrons. This place right here is missing it. So it makes sense that this part of the molecule is positive and this side is negative. Okay? Now, if I unshare this screen, this is what I was asking you to do in lab today. Okay? I would take a connector and I would put, okay, it says in my list, and I don't have the lab in front, but I believe the white is the hydrogen. Okay? So I put my white hydrogen here. And then the green is a halogen. And I put this together, and you can see that this model, although very straight, and it gives you an idea of the shape, linear, that is not the same on both sides. Okay, now it's easy to see this one and feel this one and not have to do this one, but I want you to go through the steps. So clearly this shape between two atoms can only be linear. And clearly the atoms are different. And this bond would be sharing electrons closer, in this case, to the what? To the halogens or iodine side, making this side of the molecule the negative side, this side the positive. Now, when we have more than one, okay, bond, that other polar bond could, in fact, cancel it out if it's symmetrical. We'll see that example. So let's continue on. And let us continue to share the screen here, screen share. Let's go back to where I was. And the screen, and let's go back to where I was here. Okay, so back to CH4. Oh, say the geometry. The geometry is linear. Not too bad, right? So the key for number one is if you only have one bond, and the bond is polar, the molecule has to be polar, because what makes a polar molecule is that polar bond. It creates that unequal distribution of electrons. And again, there's a lot of implications for being polar. Okay, again, our body, for the most part, deals with a lot of things that need water, which is polar, to help break down and move around, ions and sugars and carbohydrates and those kind of things. So moving forward, it's important. So here's CH4, otherwise called methane. How do we do a Lewis dot diagram? I start with my C, has 4 valence electrons. And then I have my H, okay, who has its own valence electron. And you can see this is a nice pairing, isn't it? What's nice about this is that if I look, each hydrogen feels like it has 2 by sharing. It brought 1 to the table, and now by sharing it feels like it has 2. So each of the hydrogens are now stable, low energy, just like helium. And of course, the carbon, by sharing its 4 electrons with the 4 individual hydrogen, feels like it has 8 by sharing. They're forced to share because they both have what? High electronegativities. So the first question I give to you, what's the bond type here? What's the bond type? That's right, the bond type. The bond type, of course, is going to be polar in this course. Now, why polar covalent? Because they're sharing unequally. Now, carbon and hydrogen have very similar electronegativities. Carbon is about a 2.6, hydrogen is about 2.2. So that pair of electrons is going to be slightly closer to the carbon side than the hydrogen side in this covalent bond. So this side of the bond is a little bit negative. This side is a little bit positive. And guess what? We have differences because there's an unequal distribution of electrons across this bond. So we say it's a polar covalent bond. Now, I didn't write covalent before because don't have to. You never can have an ionic compound or bond that's polar. Ionic is ionic. As I said yesterday, asking if an ionic compound is polar is like asking number 5 its marital status. It doesn't make any sense. Ionic compounds are crystals or ions. They're not individual particles. Okay, so back to what we're doing here. What's the molecule type? Well, to be polar, right, we have to have an unequal distribution of electrons. So we have to have a polar bond. Check. We have a polar bond. We have 4 of them. So this has a chance to be polar in terms of the entire molecule. Question is this asymmetrical, right? To be polar, you have to be asymmetrical and you have to have polar bonds. Okay, well, this has polar bonds, no question. And we say because it's the same all the way around, it is very, very nonpolar. These 4 polar bonds cancel themselves out. Now, why do they cancel themselves out? Well, they do so because in every direction, we have the same polar bond. We have the same unequal sharing occurring in all directions. And if that's the case, no one side has a different type of electron density than another. The weird thing I said yesterday, I'll keep saying, this molecule is equal in its unequalness in all directions, which means no side is different and you don't have any poles. Remember, poles or dipoles or polarity means you have differences. So the molecule type is nonpolar. We can say that the dipole moments cancel out, those arrows we drew. We can say that the polar bonds cancel out because it's symmetrical. But what makes more sense is the idea when you see the structure. It looks like it's flat, it's not. So let's look at the structure again. All right, so I'm going to pick a carbon atom, and my carbon atom in my thing here is black. And if you notice in the black beads that you can do your lab, and I want you to build these for each of these because you can get suckered into thinking that the structure that you drew from the Lewis dot diagrams is exactly how it exists in nature. This, as you remember, a 4-sided object isn't planar, okay? We see it on the paper like this. Now let's put the H's in, all right? We're putting the H's into, and the rule when you do this is you put the sticks into the holes, and you always have to fill in all the holes. Sometimes you don't put the atoms, okay, or the beads here, or these little round spheres, okay, into all the sticks, and I'll show you an example. So this is what I'm drawing. This looks a lot different than what is on your piece of paper, and it can confuse you. On your paper, and I did this yesterday, okay, it looks flat. So if I hold it like this, you could be suckered into thinking it's flat like this. Now in this case, it so happens being flat would make it symmetrical, but there are some examples where it doesn't. So this is a very symmetrical atom, and think with me, I've got 4 polar bonds that are all the same. So it is unequal sharing in all 4 directions. That's the same. So it's unequal, it's equal in its electron density all the way around, because these 4 polar bonds are spread out evenly all the way around. So this molecule becomes very nonpolar because this side isn't any different from this side or this side or this side, because of the same same polar unequal sharing in all directions. So it has polar bonds, but doesn't mean it's going to be a polar molecule. In this case, because of the shape is symmetrical, the polar bonds cancel themselves out, and there's no one side that has an advantage. Therefore, it's nonpolar. Okay, so back to sharing. Let's go on to the next one. All right, hope that makes some sense. I'm just checking to make sure there is no questions here. Okay, now let's go on to the geometry. We learned this. The geometry of the 4-sided object is a tetrahedral. And this is how I want you to do your lab. I want you to build the structure before you answer whether it's a polar or nonpolar molecule. Okay, you must look at the 3-dimensional structure and think 3-dimensional. Moving forward. Okay, iodine, I2. All right, we have 1 iodine. It has 7 valence electrons. And we have another iodine that has 7. And I'll just draw different colors to show that I'm using up all the electrons. I put out all the valence electrons, and I put 1 of each to make a bond, and then I evaluate. Each iodine feels like now it has 7. Okay, so look at this bond. Is this bond being shared equally or unequally? Equally. This is equal sharing, party people. Why is it equal sharing? Because it's the same nonmetal. They have the same electronegativity. If this is 2.8 and this is 2.8, it might be 2.7, but it doesn't matter. If they're both the same, then no one's pulling on those electrons anymore. They're shared right down the middle, and this side of the bond doesn't have more electrons than this side. And there's no difference. If there's no difference, there's no poles, there's no polarity. Polarity means different. So we would say that this is a nonpolar covalent bond. Now you could try to remember this. Same nonmetals are forced to share equally, must be nonpolar. And if it's different nonmetals, because of different electronegativities, is polar. Be my guest, but you have to understand why. You have to equate this equal sharing if they're the same nonmetal, and then unequal sharing if it's not. Okay, molecule type. Well, my friends in chemistry, this doesn't have a polar bond. To be a polar molecule, you have to have an unequal distribution of electrons somewhere, and that occurs by polar bonds. This does not have a polar bond, so it could never, ever be a polar molecule. Besides, isn't it symmetrical, the same all the way around? So this is a nonpolar, I guess it's right here, we're doing it, confusing myself, nonpolar, and the molecule is nonpolar. I don't think I have to do the 3-dimensional structure. So it's nonpolar molecule. And again, you better understand the difference between the bond and the molecule. They are different. You need to have a polar bond to have a chance to be polar. Molecule. But like I just showed you, having a polar bond doesn't mean that the molecule is automatically a polar molecule. All right? NH3. Again, these are ones we've done before, but hopefully we can understand these better. We have N has 5 valence electrons. All right? Each H has 1 valence. It's a nice pairing. It's the reason why NH3, which is called ammonia, it exists as NH3. It needs 3 more electrons to be shared to get what we call that octet, that number 8 that makes it as stable as a noble gas. Each hydrogen wants to fill its energy level, which is 2, and feel like it's helium. So a great pairing here. Everybody is stable and has their filled energy level filled, and this is how the Lewis dot diagram works. Now, you don't have to have circles, but we use circles to evaluate. Now, my first question is, what kind of bond do I have between the N and the H? They're all the same. And if you said polar covalent bond, you would be absolutely correct. I would always ask you, why is it a polar covalent bond? Because it's 2 different what? Nonmetals sharing how? Electrons unequally. Nitrogen is much more electronegative than hydrogen. Nitrogen, okay, is about a 3.0, okay, and again, hydrogen is about a 2.2. So clearly these electrons are being shared unequally toward the N side. So just considering the what, you have to understand, we're talking about bond, this nitrogen side is a little more negative compared to the hydrogen side because that pair is closer. That's why. All right, now just because we have 3 polar bonds doesn't make the molecule have to be polar, correct? Just because you have a polar bond doesn't make it polar. You have to have a polar bond in order to have a chance to be a polar molecule. So we have polar bonds. So that's a check. Now we have to consider the 3-dimensionality. Now you can look at this and say, is this the same all the way around, right? The second law is measuring, is this asymmetrical? And we look at it and say, yeah, it looks asymmetrical the way I have drawn it. Looks like it's not the same all the way around. So according to the way that I drew it, this looks like it's asymmetrical. But what does that mean? Being asymmetrical means you're going to have an area in the compound with more electrons than the other, unlike what we did before with CH4. But just to make sure, so you can visualize what this looks like, let's go back and build this molecule like you should be doing in your lab with the molecular model kits. So I'm going to go find nitrogen, and my nitrogen here is blue. And like I said before, you're going to fill in all of the holes. So I'm going to fill in everything I have. And I built this for you yesterday, I believe, with the balloons. I have 4 balloons. Notice there's 4 holes. This represents the 4 pairs of electrons that nitrogen had. So there it is. That looks eerily similar to a what? Tetrahedral, if you consider where the electrons are. 4 balloons yesterday pushed each other into this shape. Now, I'm going to put some hydrogens here, which are the color-coded to be white. And it was NH3. And when we do that, we get this shape here. And what is that sticking out? Well, that's a lone pair. And that lone pair pushes the other 3 down. It's called VSEPR theory, not required. But you can clearly see this is the 3-dimensional structure. On paper, okay, we're looking at what? Something like this. And we see 3. You look at it and you see 1 on top and 2 on the bottom. It's really not flat. It's like this. It's a top of a 3-sided pyramid. What's the word for the shape of this? You're responsible for it in my course. This is a triangle on top of a pyramid. So this is triangular pyramidal, or trigonal pyramidal if you want to sound fancy. If you sound fancy, pinky up. Okay, all right. So in any case, look at the shape. Is this symmetrical, considering where the atoms are? It's not. It's symmetrical where the electrons are, but we consider the atoms. Look with me, guys. Look carefully. I'm going to put it on its side. The nitrogen side here is more electronegative. Okay? And that pulls in the electrons in toward the N side. And it leaves the H side right here more positive or electron less. Its density is less. So this is the positive side of the molecule, and this is the negative side of the molecule. And that is a polar molecule that interacts very well with water and other things that have negative and positive ends. Okay, continuing on. Screen share, let's go. I think last couple. I'm gonna start going quicker now. And let's go there, and let's go to here. All right, let's finish this out. Share. N2. Okay, we built this one a couple times before in different ways, but N has 5 valence electrons, and some people would have trouble with this. So we draw it like this, and this N has 5 valence. And what we do is we make one bond, right? Always start with a bond, and then we evaluate. When we evaluate, you'll see that this N, 2, 4, 1, 2, 3, 4, 5, 6 has 6 electrons. This N has 6 electrons. Not good. They want to have that full octet, the second row element. The only thing you guys can do to satisfy that is to pull these guys together. So I put another bond together. So the only thing you can do to try to help this is add another bond. Now this is a second bond, right? A second pair is a second bond. Now we have 1, 2, 3, 4, 5, 6, 7. Each N has 7. Still not there. What can we do? We make another bond, or we put another pair together. You can see that there's what? 3 pairs of electrons being shared, so that each N has what? 1, 2, 3, 4, 5, 6, 7, 8. All right? And this says that nitrogen has a triple bond to make this work. Absolutely. All right? And some people would say, well, if these electrons repel these outward, it's not important to know this, but what happens is these electrons would probably be pushed out. Okay? And if you don't do that, it's okay. All right, as long as you show that full octet and 3 bonds, but there are 2 lone pairs here. So the first question I have for you guys is, what kind of bond do we have? Oh, by the way, the geometry of this one was trigonal, the one we just did, pyramidal. Okay, and if you said triangle, pyramid, I accept that. So number 5, bond type. Same nonmetals with the same electronegativities would be sharing equally. So this would be a non-polar covalent bond. And the molecule type would have to be non-polar, right? Why? Why? Because you don't have a polar bond anywhere. There's no unequal distribution of electrons anywhere in this. So how could it ever be polar? Not only that, if you want to think of it this way, it's symmetrical on both sides. And of course, the geometry of 2 atoms can only be linear. Now, I'm going to draw this one. I'm going to build this one only because some people, when they do the kits, don't know how to make a triple bond. So my end is a blue, and of course, the kit I have only has 1 blue. All right, so I'll do my best. I'm going to use yellow, I guess. All right, so use the bendies. The bendies are for the triple bond. So here's 1 bond. Okay, another bendy would make another bond. So I'm making there's a double bond, right? So that's how you would do it in your lab today. And then you would make another bendy into a triple bond. And that would be how N3 looks like according to this kit anyway. Now notice there should be 1 more bond being pointed out. I'm just going to show one side. And that shows the lone pair that I was talking about. And then you'd have another one here. But in any case, that's how you build a triple bond. It's a model. You can see it's linear and very symmetrical. So back to screen sharing one more time. Okay. Last one might be the most complicated one. So I just want to hit this one, and that'll call that a day with me trying to teach you. And you're on your way to your lab after this. So let's get rid of this. Let's go to silicon dioxide. Okay, now silicon is under carbon in the periodic table. So you should notice something. If silicon, all right, is here, right? It's under carbon, so it's going to make very similar chemical what? Compounds. We did carbon dioxide yesterday. Well, silicon dioxide will be essentially the same. That's what Dmitry Mendeleev was finding, that they saw these chemicals were reacting the same and making very similar compounds because of the same valence electrons. So silicon and carbon are essentially the same valence electron-wise. Their structures will also be similar. Okay. I don't know if you probably didn't see that because I'm not sharing that screen. But in any case, here we go. Silicon. It has 4 valence electrons, so I write it out. Oxygen has 6, so I write it out. 1, 2, 3, 4, 5, and 6. This oxygen, 1, 2, 3, 4, 5, and 6. The first thing that I do is what? Make 1 bond. And then I evaluate. Put out all the valence electrons, and then I evaluate. So I'm going to evaluate. This oxygen feels like it has what? 1, 2, 3, 4, 5, 6, 7. Same thing for the other side. And silicon in the middle, by sharing, feels like it has 1, 2, 3, 4, 5, 6. Not going to work. What can we do? That's right, Tahira. We put another bond together, another pair together. All right. And we do that to one side. We're going to try it to another. We're going to keep it very similar. Put another pair here. And when we do that, you'll see, we're always going to remind you of what CO2 looks like. So we're back to evaluating, and we can see now this oxygen, like the one on the end, 1, 2, 3, 4, 5, 6, 7, 8, has its full octet. This one has its full octet. And now silicon, if you count, 2, 4, 6, 8, by sharing, has its full octet. All right, so that is the Lewis dot diagram. You don't need the circles, but they help you to make sure that you have the right number of electrons being shared. Okay, bond type. All right, well, 2 different nonmetals obviously have to be sharing electrons unequally, so it's a polar covalent bond. The molecular type. Well, the molecular type here, I have to know the shape. It does have polar bonds, so this could be polar, but is this going to be a linear shape or a bend shape? How do I know? And yesterday was the key. If there were lone pairs of electrons above and below the silicon, it would bend these downward, but silicon doesn't have any lone pairs to push it down, so this is going to stay linear, right? And because it's linear, we would say that the amount of electrons on this side is going to be the same as this side. There's no poles because the 2 polar bonds are being symmetrically distributed. So this has polar bonds. The first law is satisfied, but this thing is symmetrical. It's the same all the way around. Therefore, the polar bonds cancel. And this has no different side to it, no poles. This is a non-polar molecule. Okay. Now, as a quick review, this is a polar molecule. The negative part would be up top, so we kind of point to it. That's a dipole moment. And then we only had 2. We had HI and NH3 is our polar molecules. Now, yesterday we had water who had lone pairs and it was bent, and you'll see that. I'm not going to draw that for you, but you should realize that silicon is going to have 2 bendies going this way when you try to build this chemical. And the 2 lone pairs should be sticking out to show the 3-dimensionality. Hope that helped. Go take your break if you're Ms. Rosenberg lets you, and come back, and I want you to open up your labs. Each lab group, please take a molecular model kit. Please don't build a super atom or a dog or anything like that for me to take apart. And I want you to build the atom, write the Lewis dot diagram, and predict the geometry, the bond type, and the molecule type. Okay, we're going to have a rat on this Monday. So I don't have anything assigned other than you going over these lectures and your worksheets and the keys. Have a great weekend. Thanks.